Now let me explain to you why subtracting lambda from the diagonal trick works for finding eigenvalues. So A, B, C, D, setting this equal to 0 to the eigenvalues. Right, that was what I claimed. So let me explain to you the theory behind this. Right. Suppose we're given A, B, C, D. And our goal is to find the eigenvectors and eigenvalues. What's the definition? By finding eigenvectors, I mean two values, L and M. So I'm looking for a single vector, a column vector, which satisfies the following condition. Multiplying the matrix to the vector is like multiplying a number to the vector. If such a thing works for at least one of Lm is not equal to 0, so that's the condition. So of course this is always true if you plug in 0, 0. Isn't that true? If you multiply 0, 0, then any matrix times 0, 0 gives you 0, 0. Any scalar multiple of 0, 0 is 0, so it really doesn't achieve anything. That's something that we already know. But I'm trying to say that if there is a pair of numbers which makes these, at least one of them non-zero, and this still works, that's something. Actually, we know where it was used. I demonstrated that such kind of vectors and eigenvalues were used to solve system of differential equations. That's the reason why we're trying to learn about this, right? So that's what we want to do. But think about what this is really saying. This is saying across down, so I get AL plus BM. Then across down I get CL plus DM equal, on the right side, lambda times L, lambda times M. So this single matrix equation is really talking about this system, right? Isn't that right? Yeah. Okay. Now look, if I move this to the other side, and just for the moment treat A, B, C, D, and lambda as some given numbers, and look for L, M as unknowns. So we're going to move this over here and factor out the L. So we get A minus lambda times L plus Bm equal to 0. CL plus D minus lambda times M equal to 0. And this is equivalent to the previous one, because all I did was I just moved this over to the other side. Okay. Now, this thing looks a lot like this, right? But to really see what's going on, you want to go back to the matrix notation. So how do you write down this as a matrix equation? You write down a matrix of coefficients and write down the matrix of unknowns. L and M are the unknowns that we have, right? And then you write down the constants on the right side. Because this is 0 and 0, I should put 0, 0. Now, can you read this system and figure out what should go in this matrix?
A minus alpha.
A minus lambda.
B.
B.
C.
C.
D minus lambda.
D minus lambda. Do you agree? I mean, if you didn't get what Maxwell just said, just think about this. This times this makes it A minus lambda times L, B times M, which is exactly this first part, right? And we're setting that equal to 0. All right? And same thing here. If I multiply across down, you get this one. Okay. Now, we also learned about this thing called inverse matrices. It's something that you learned in Calculus 3 but forgot. Do you remember how to do inverse matrices? It's something like this. You do 1 over the determinant, and you switch these two around, right? And you negate these other ones, right? You remember that? That's how you remember. You remember learning it. You don't remember the actual thing. Okay. Still fine. We don't really need to remember everything. So we have this inverse matrix, and we can just multiply this both sides to get rid of these and solve for L and M. Now, what would you get for L and M if you did that? On the right side, even if you totally forgot what that formula was, on the right side is some matrix times 0, 0. What would that give you? 0, 0. Now, is that good? Not good. Why not good? Huh? Because our definition of eigenvectors stated that we can't have both of them 0. Okay? So this is actually not the desired outcome. Okay? And therefore, so it's this part is a little bit convoluted. The argument is a little bit convoluted here because it seemed like, oh, we're trying to find out what the eigenvectors are. In other words, I want to find out L and M are. So you work all the way through and ended up getting the result that you didn't want, and you have to go back and look where things went the wrong turn. Where's the part that we made a mistake here? Can you find out? This is okay. That's okay.
Both equal to 0.
Hmm?
Both equal to 0.
Both equal to 0? What do you mean? No, it should be. I moved this over here, moved it here, so everything's good.
So the thing up there equals 0? Or is it supposed to be equal to 0?
No, I didn't get to here yet. So for the moment, yeah, just forget about this. So here's the problem. I want L and M. I tried my best and found out that L and M can only be 0. Is that right? Is this the only possibility? When would this kind of calculation fail? Yeah, that's why this argument is a little bit convoluted. But if you have enough experience with matrices, you know that actually not all matrices have inverse matrices. That's the key. When does a matrix not have an inverse matrix? You know that? When does a matrix not have an inverse matrix?
The determinant 0.
When the determinant is equal to 0. See, this is a determinant, right? 1 over d. If this determinant is equal to 0, then you can't do 1 over 0. That's not allowed. Therefore, such an argument will fail. Now, do we want this process to fail or succeed? No, that's the convoluted part. We actually want this to fail. Why? Because we want L and M to be a non-zero solution to this equation. So here's the argument. If this did succeed, then we don't get what we want. So we need this to fail. Okay? And therefore, the only way that you would get an eigenvector is when the determinant of this thing is equal to 0, and that's why this should be 0. Okay, that's the argument. You got it? Okay? Makes sense now, right? Okay. So that's where we had, and by the way, along the way we found out something more. I kind of erased parts of it, but if I rewrite this over here, this is the equation that we get. We get A minus lambda B C D minus lambda times LM equal to 0, 0. And if you think about it, this was equivalent to AV equal to lambda V. We started from this and we made a bunch of transformations and ended up with this, right? And when in practice, when you try to find the value of L and M, you will find that instead of writing it this way saves you time. They're equivalent things. If you write it this way, then you have to move things around and sort things out before you solve. Here, everything is sorted out so that you have 0, 0 on the right side. So this is actually a better one to solve. Okay? So that's another bonus that we found out while following this argument. So, here to review what we just said is the following. The only way that you could have a non-zero eigenvector satisfying this equation is that this determinant has to be 0. And for those lambda values that you get, you can plug those in, and you'll see that for those, you're going to get some non-zero solutions of this. Okay? Now, I also talked about how this second equation will always turn out to be the same as the first one if lambda was a solution to this. Okay, so let me explain that part also. That actually relies on geometry. See, if you think about this as x and y, and you just say A, B, C, D, where A is this, B is this. Okay, you can think of it that way, right? And equal to 0, 0. Then if you do a cross down for each of them, you get AX plus BY equal to 0 and CX plus DY equal to 0. Now, the geometric argument goes like this. What kind of graph does this produce? It's a straight line going through the origin, 0, 0, right? That's another line that's going through 0, 0. Now, what if these two are two distinct lines going through 0, 0? Now, where is the common solution? 0, 0. So if this was really two different lines, what's the only solution? 0, 0. Is that what we want? No, it's not what we want. So what's the only other way for this to have a non-zero solution? When they are exactly the same line. Okay? Then you have infinitely many solutions. That's why for a given lambda value, there are infinitely many solutions which are multiples of each other. Because it's all along this single line passing through the origin. That's why. Okay? So because of that geometrical insight, you know that for a lambda value that satisfies this, it will definitely give you two line equations that are basically the same thing. That's why you only need to talk about the top one. Right? And if you do the top one, then and just find out two pair of numbers that satisfies it, because there are infinitely many, you just need one pair. One pair of numbers that satisfies it, that's what we want to use for the eigenvector, for the eigenvalue. And that's the theory behind everything.